Okay, we will go through some important points in the class 12 chemistry chapter 4 chemical kinetics. The feasibility of the chemical reaction which can be predicted when delta G is less than 0 means the reaction is feasible. Okay, delta G less than 0 reaction is feasible. Branch of chemistry which deals with the study of the reaction rates and their mechanism is called chemical kinetics. So here it's feasible to convert a diamond to graphite, but it is so slow that is not perceptible at all. Okay, it's thermodynamically feasible, but conversion is so slow that is not perceptible at all. See, there is this example of a slow reaction, fast reaction. Precipitation of the silver chloride occurs instantly by mixing the oxide silver nitrate with sodium chloride. This is instant, fast reaction, but the slow reaction is resting of the ion in the presence of the air and moisture. Okay, this is slow reaction. The rate of the increase in the concentration of any one of the reactions. Now the rate of increase in the constant of the any of the rate reaction. Okay, 1 mole of the reactant produces 1 mole of the product. Okay, the square bracket represents the concentration. Okay, the rate of disappearance of the reactant equal to rate of appearance of the product. Okay, rate of appearance of the product. Disappearance is equal to the appearance. Delta is a negative quantity. Concentration of the reactants is decreasing as the reaction progresses. Okay, it is multiplied by -1 to make sure the rate of the reaction positive quantity. This is how the concentration of the reactant decreases, whereas the concentration of the product increases in a chemical reaction. The concentration of the gases is expressed with the partial pressures. Okay. Then the experimental data, how they are computing the average rate. So the difference in concentration divided by difference in time. So okay, then you will get the average rate. Instantaneous means at that point. So here at t equal to 600 seconds, this is how you compute the instantaneous rate. That is change in x-axis divided change in y-axis. Okay, how much change in the y-axis, how much change in the x-axis at that point of time. The rate of disappearance of any reactant is same as the rate of appearance of the product, because reactant is converted to the product. So here in this reaction, this 2 is the stoichiometric coefficient. So when the rate of appearance of the product divided by the respective of stoichiometric coefficient. For expressing rate of the reaction in which reactants where stoichiometric coefficients are not equal to 1, then we have to divide by that stoichiometric coefficient. Here 1 by 2 equal to this, like this, the rate of the reaction. We have to convert this reaction to the rate like this. For a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of the species, and hence the rate can also be expressed as the rate of change of the partial pressure of the reactant or the product. Concentration for the liquid, this is for the gases or the partial pressures. Rate of the reaction depend upon the experimental conditions such as the concentration of the reactants. In case of gas, it is pressure, the temperature and catalyst. The representation of the rate of the reaction in terms of the concentration of the reaction is known as the rate law. Okay, it is also the rate equation or the rate expression. It will show the rate of the reactions decreases with the passage of time. Okay, because the reactant concentration decreases. This is general form of the equation where A, B, C, D are the stoichiometric coefficients of the reaction. So this rate law can be expressed the concentration of the reactant to the power, okay, where x and y may or may not be equal to the stoichiometric coefficients. So this power x and y may not be equal to this ABCD. This is the rate equation. The form of expression 4.4 known as the differential rate equation where k is the proportionally constant rate constant. The rate law is the expression in which reaction rate is given in terms of the molar concentration of the reactants. This is the concentration of the reactants with each term raised to the some power. This is the power which may not be same as the stoichiometric coefficient. This power may not be same as this ABCD coefficients. So this is how you compute the rate of the reactions. So here this reactant concentration is changed and the rate is measured. So here they are changing the concentration of the NO and keeping the oxygen concentration constant, and they are measuring rate is 4 times. Now they are changing the concentration of the oxygen, keeping this rate same 0.3, now 2 times, is 4 times and is 2 times. Based on that they arrive at this rate equation like this. The exponent of the concentration of the terms are not same as this one. Okay. Rate law for any reaction cannot be predicted by merely looking into the balanced chemical reaction. That is theoretically, but must be determined experimentally. Order of a reaction. Okay. So this power x plus y gives the overall order of the reaction, where x and y represent the order with respect to the x order respect to A, y order respect to B. The sum of the powers of the concentration of the reactions in the rate law expression is called the order obtained by the chemical reaction of that chemical reaction. Order of the reaction can be 0, 1, 2, 3 or even a fraction. A zero order reaction means that the rate of the reaction is independent of the concentration of the reactants. A zero order reaction means that the rate of the reaction is independent of the concentration of the reactant. Okay, here they are just adding the power rate. This is second order, this is half order. The reactions taking place in one step is called elementary reaction. Elementary reactions are one step reaction. When a sequence of elementary reactions called mechanism gives the product, the reactions are called complex reactions. So complex reactions having a sequence of elementary reaction. This is the unit of the rate constant for zero order, first order and second order reactions. Molecularity of the reaction, the number of reacting species, atoms or ions taking part in the elementary reaction, which must collide simultaneously in order to bring about the chemical reaction is called the molecularity of the reaction. Unimolecular is one reacting species is involved. This is unimolecular, this is bimolecular, 2 molecules, this is trimolecular, 3 molecules. The probability that more than 3 molecules collide and react simultaneously is very small. Okay, very small. More than 3 molecules colliding simultaneously is very small. Hence, the reaction with molecularity 3 or more than 3 are very low, very rare and slow to proceed. Even for the complex more than 3 molecule, the segregation must take place to more than one step. See the above reaction, this reaction which apparently seems to the 10th order, because 1 plus 6 plus that is 7 plus the 10th order, but is actually a second order reaction, because it takes place more than one steps, and the slowest step determines the rate of the reaction. Rate determining step. The reaction is controlled by the slowest step in a reaction is called the rate determining step. The first step being the slow as the rate determining step. This is rate determining step. Order of a reaction is experimental quality, it can be 0 or in even a fraction, but the molecularity cannot be 0 or non-integer. Molecularity cannot be 0 and non-integer. Order is applicable to elementary as well as complex reactions, whereas the molecularity is applicable only for the elementary reactions. For complex reactions, there is no such meaning, because complex reaction occurs in several steps. Complex reaction order is given by the slowest step, and the molecular of the slowest step is same as the order of the overall reaction. Integrated rate laws. The integrated rate equations are different from the reactions of the different reaction methods orders. Zero order reactions mean that the rate of the reaction is proportional to the zero power of the concentration of the reactant. Okay, see here 0 power of the concentration reactant, but anything power 0 is 1. So that means here for zero order reaction, how the concentration related to the rate constant. This is the time versus concentration of the ore for the zero order reaction. Concentration of decreases over the time. For the zero order reaction, because this power 0, anything power 0 1, then rate constant equal to rate of the reaction equal to rate constant for the zero order. Rate of the reaction is independent of the concentration. Okay, this rate is equal to rate constant independent of the concentration because of the power 0. First order reaction. First order reaction is this one. This is an example of a first order reaction. These are the curves. First order reaction between time versus, this is natural log of the concentration, decreases over the time. And these versus this is for the first order reaction. Half-life of a reaction. The half-life of a reaction is the time in which the concentration of the reactant is reduced to half of its initial concentration. This is concentration becomes 50% in this time, half-life time. So from this equation, it is clear that for a zero order reaction, the rate this T of is directly proportional to the concentration of the initial concentration of the reactant, and inversely proportional to the rate constant. Okay, T of the zero order reaction directly proportional to the initial concentration, inversely to the rate constant. But for the first order reaction, the T of is a constant because it is not related to the concentration of the reactant here. Can be seen from first order reaction, half-life period is constant, that is independent of the initial concentration of the reaction. Zero order reaction half is directly proportional to the initial concentration of the reaction. For the first order, it is independent of the concentration of the reactant. So here the T of to complete 99%, it takes 10 times the first order reaction time required, 10 times then of the first half life. See, from 100% to 50% is T of time, then 50% to 25%, then 1 T of. So in that 10 times it takes to achieve 99.9%. See here, if you take two reactants, one of them is taking excess, this reaction will become as a first order reaction. Will behave as a first order reaction because this reactant is taken at excess and this is very small amount. So this change in this reactants is not noticeable. So that is why it's the first order reaction. Temperature dependence. For a chemical reaction with rising temperature by 10, rate constant is nearly doubled. We raise by 10 degree, rate constant nearly doubled. The temperature dependence of the reaction is accurately measured, explained by the Arrhenius equation. This is that equation. Okay, A is the Arrhenius factor or frequency factor. The energy required to form the intermediate activation complex is known as activation energy. This is the energy, activation complex. This is the forward activation energy, this is a backward activation energy. Some energy released when complex decomposes to form products. Okay, from this complex decomposes, here see it is releasing energy. So energy is decreasing before forming the product. Okay. So here this fraction of molecules, the number of Ne means number of molecules at this energy, then Nt total number of molecules. This is the most probable kinetic energy. This peak is most probable kinetic energy. This is the Maxwell-Boltzmann curves. The area under the curve in this temperature is same as this temperature. That is total area under the curve same. But the number of fraction of molecules after the activation energy is more when temperature is high. This is T plus 1. Here you see this area is more than this area. Fraction of additional molecules. Okay. The area under the curve must be constant for both the temperature. The factor in this represents the fraction of molecule that have this area. That represents this factor in the Arrhenius equation. Fraction of molecule. This is the activation energy. After that activation energy, these molecules have a higher more than the activation energy. Now that Arrhenius equation, that increasing temperature decreases the activation energy. See, this activation energy is decreased, increasing the temperature. Temperature or that increasing temperature or decreasing active energy will result in the increasing the rate constant. Okay. Because this is the above is the negative sign. So when you increase the temperature and you decrease the activation energy, the negative quantity, that means rate constant will increase. Effect of the catalyst. A catalyst is a substance that increases the rate of the reaction without itself undergoing a permanent chemical change. Okay, this catalyst reduces the activation energy of the reaction, but it does not change the Enthalpy of the reactions does not change the delta G, that is gives the energy of the reaction. It does not change the equilibrium constant. Okay, does not change the delta G. It does not change the equilibrium constant, but it lowers the activation energy. You see, the activation energy is lowered for using catalyst. Okay, see, it provides a different path for the reaction. The number of collisions per second unit volume in the reaction mixture is known as the collision frequency. Represent the collision frequency of the reaction here, represent the fraction of the molecule of the energy equal. Collisions in which molecule collide and sufficient kinetic energy and the threshold proper orientation, that is also important, so as to facilitate the breaking of the bonds between the reacting species and the formation of the new bonds in the product is called the effective collisions. This is the effective collision. Okay, with proper orientation, products are formed. This is improper, then no products will be formed. Okay, molecularity and the order of the elementary reactions are the same.